Okay, so hello everyone, and welcome to another topic of our course, and this one is entropy. So this is the last part or last chapter in the first part of the subject on basic thermodynamics, and it essentially completes our theory for most practical purposes. So we still need the third law of thermodynamics technically that we will see later, but that's not going to be used so much. So okay, let's see what this chapter is about. It's very brief, but like I say, it's very important as well. So we will begin by stating and proving Clausius' theorem. This is a direct consequence of Carnot's theorem, and it basically establishes an inequality that holds for any process. And from this inequality, we are going to be able to define a new thermodynamic property or function of state, just like the internal energy, just like we did with adiabatic work. So this new quantity is going to be called entropy. So we will define entropy. So how we define the entropy of an equilibrium state of a thermodynamic system. We are going to see generalization of the expression in Clausius' theorem, generalized Clausius inequality, just in differential form. And we are going to see, as another property of entropy, the additivity of entropy, or rather, when does it hold that entropy is additive. Then we are going to move to consider the maximum entropy principle. That's also a consequence of Clausius' theorem, and in particularly it follows clearly from the generalized Clausius inequality. This maximum entropy principle is absolutely central in thermodynamics. So later on, everything that we'll do is going to be based in this maximum entropy principle, or its conjugate variant when expressed in terms of energy or any energetic property of state, which would be the minimum energy principle, or the minimization of other thermodynamic potentials. We are going to learn this when we study thermodynamic potentials. Well, so this is absolutely key in thermodynamics. And as an application of the introduction of entropy, we are going to actually prove what we saw from the famous historical experiment by Joule, where he saw experimentally that in the ideal gas limit, the internal energy of a gas only depends on temperature. So actually you don't need to go to experiment to see that. You can actually prove it once you know what entropy is and you know how to work with its mathematical properties. Okay, so yeah, let's go directly straight away into Clausius' theorem. This first video is likely going to be a little bit longer than they are usually, but it seems impractical to me, at least, to break Clausius' theorem. So let's just see what the theorem says. So I would just read it because I wrote it here before to save time. So let a system undertake an arbitrary cyclic process in which it absorbs amounts of heat equal to, say, Q1, Q2, Q3, up to Qn. So there are n of these strokes in which the system is absorbing heat from heat sources at temperature T1, T2, T3, Tn, respectively. Okay, so then the sum of the heat absorbed in each of these strokes, normalized by the temperature of the bath from which heat is being absorbed or into which heat is being released, is a negative number. Okay, if you sum over all those strokes, you get a negative number always. Okay, and then you can do a corollary to this, and you can see that the equality here holds when the cycle is reversible. Okay, so kind of similar to Carnot's theorem, and we are going to see this is really a direct consequence of Carnot's theorem. So before we really start to prove the theorem, let's just see one of such cycles, just to have a concrete picture in mind, and this will help us fix ideas. So let's think, of course, as usual, simplest system. So a single component expansive system in the VP representation. So that's what we have there. And imagine that we have maybe 3 baths. So let's discuss a cyclic process in which the system is only in contact with 3 temperature levels. It could be many. In particular, actually, there could be infinitely many of them. Okay, so I say n here, but this n could be infinity. So let's put just 3, and let's draw just quickly here some kind of isotherms at 3 different temperatures. So this would be a low temperature. Then we can make an intermediate temperature, say up here, and then we do a high temperature isotherm somewhere there. Okay, fine. So we can say this is T2, and this is T1, and this is T0. Yeah, maybe if it's blue, it's more consistent. Okay, good. So we can make any cycle you like, really. I mean, this is just made up. It doesn't really matter as long as it's a cyclic process. It doesn't have to be reversible. Okay, so it's any cyclic process. So imagine we start our path in this state 1 here, and we go down the isotherm doing a quasi-static process. Okay, so we stop here in equilibrium state 2. During this stroke, the system is coupled to a heat bath, so to this heat bath, and it will exchange certain amount of heat with it. So that amount of heat goes into this expression here. Okay, so that's the first contribution to the expression, that heat divided by that temperature. So now we can do whatever you like. So imagine, for instance, that we do now an adiabatic process, and through this adiabatic process we go down to this temperature here. And maybe we do this adiabatic process quasi-statically, why not? So that would be a continuous line representing an adiabat that will join state 2 with state 3 down here. Okay, and now maybe imagine that what we do here is we keep the system in contact with, so we remove the adiabatic insulation, and we keep the system in contact with this heat bath at the intermediate temperature T1, and we do an expansion, but this expansion we do it not quasi-statically, but actually we do it quite fast. So the system in between, I'm putting a dotted line here to represent a non-equilibrium process, is just out of equilibrium, and it just lands finally on this final state at this volume here. Okay, so now imagine that we lock the position of the piston in place, and we remove this heat bath, and suddenly we connect the system to this lower temperature heat bath. Okay, and the volume is kept constant. We learned in the past chapter that this process as well is out of equilibrium. Okay, because we are not taking infinitely many baths to go spanning all the range between T1 and T0. We just use this bath first, and then we suddenly put the final temperature bath. Okay, so this process here is going to be also out of equilibrium. Our system lands in this state here, and then, I don't know, imagine that we do an isothermal compression, and we do it quasi-statically, like this. So we go there, and here in this state 6, imagine we do the same thing I just said. Okay, so after this sort of isothermal stroke, we lock the position of the piston in place here, and we connect the system to the hot temperature bath, and we let it go in its non-equilibrium kind of path back to the initial state where it began. This is a cyclic process, but it's an irreversible process. Okay, it contains some reversible strokes like this one, and this one, and some irreversible ones like this one, or that one, or the final one. Okay, there are some strokes in which the system is absorbing energy from the heat baths. Okay, so for instance, this one is one of the ones that we care about from the point of view of Clausius' theorem. Okay, so if there's some heat being absorbed by the system in this stroke, we divide by the corresponding temperature, and that's the first term that goes into this expression. Now the second stroke in our made-up cycle is adiabatic, so there's no heat. We don't count it, so we don't even think about it. Then the second stroke that we care about is this one, which is non-equilibrium. The temperature of the system is not well defined throughout this stroke, but the system is in contact with a bath with a well-defined temperature and is absorbing or releasing some amount of heat. So this heat divided by that temperature is the second term that goes into the Clausius inequality or Clausius expression. Here it is the same. In this case, I'm coupled to this bath underneath here at this lower temperature. Temperature of my system is not defined throughout, but the system is is undergoing a heat stroke, and we care about that heat divided by this temperature in this case. Then we do the compression. Again, the reference temperature is this low temperature level T0. There is some amount of heat being absorbed or released. And then we have the final stroke in which we are connected in this reference temperature level. And we are just getting there by thermalization. Okay, so in this stroke, there is also a term that comes into this sum up here. And all that Clausius theorem says is that if you do the calculation and you add up all of those contributions, you are never going to get a positive number. You either get 0 or you get a number less than 0. And in this case, because we know that the equality is only holds if the cycle is reversible, in this particular case that I have drawn here, I know for sure this is going to be a negative number. It's not going to be 0 because my cycle contains some stages which are irreversible. Okay, so now in next video we are going to prove this theorem.